All right, well, let's get started then. So this one is about large span curtain walls, reinforced curtain walls, Young's modulus, and inertia, and we're going to explain the HBS advantage here in this whole sort of topic. So a large span curtain wall could be this, for instance, where you see basically a very large curtain wall, several stories, as you can see here on the right, and it's basically supported by steel girders that are connected with steel transoms, and it's quite a lattice work really required to keep this whole thing stable. So that's an example of a large span curtain wall as you would find them currently around town, wherever you may be. Here's another one. This one is a bit more traditional, where the glass is basically framed by aluminium mullions, aluminium transoms, and in lieu of these slabs here not going all the way forward, so you can connect the curtain wall onto the slabs as you normally would, they have these steel girders here with brackets and everything to hold the whole curtain wall in place. So that's sort of like a couple of examples of typical large span curtain walls that you would find basically around. And that's pretty much what you would have to do up until Advantage came on the scene. So these curtain walls here, you can schematically show them more or less like this. So if you choose an example of 10 meters high, the red part here would basically be the steel structure that you'd have to put up with mullions and transoms in between. And on the front of that, you would essentially have the aluminium screen holding the glass. And that would be the structure of these large span curtain walls. So it could be 10 meters, it could be 12 meters, it could be 8, or whatever the size is. But that's essentially the structure that you find. Now, in section, that would look like this typically. So you would have like some big I-beams behind typically, connected by transoms, also some sort of I-beam or box profile. And then, as described, the aluminium curtain wall with glass in the front. So you'd have like a two-step structure basically, and that's what you get normally. So in Advantage, what we offer is essentially a range of larger mullions, 200, 250, 350, 450 millimeter mullions, and what that does is basically allow us to eat into that that steel structure, and in many places actually replace the steel structure. So if we look a bit at what governs the whole these large curtain walls, it's basically the SAN 613 standard, where deflection limits are set on maximum deflection for mullions or structural members. So it could be those big steel girders that we saw initially from top to bottom. It could be the horizontal girders that we saw there. Everything basically has to comply to SAN 613, and the maximum deflection is defined sort of in two steps here in the standard. So the limit is basically maximum deflection is the length of the mullion divided by 175, L over 175. You've heard of that. And that applies basically up to any mullion which is no longer than 4.1 meters. After 4.1 meters and up to 12.2 meters, it is a different deflection limit. It's L over 240 plus 6 millimeters. So, and I've just calculated here the two numbers. So for instance, at the 4.1 meter height or mullion length, the maximum deflection allowed is 23 millimeters. And so that's almost an inch basically. And by the time you get up to 12.2 meters, it's 56 millimeters. So it's significant deflections that are allowed, but it can't be any more than that. So when we start looking at this in terms of aluminium and steel structure or not steel structure, let's just look at how this deflection is calculated. So these are the simplified deflection equations, maximum deflection equations for on the right hand side here we have the steel, which is the I-beam with aluminium screen in front, and on the left hand side we have a pure aluminium Advantage construction. And the deflection here for steel and for aluminium is identical, other than at the end here you've got EI for steel, and at the end for aluminium here you've got EI for aluminium. Other than that, the equations are identical. And for these two structures basically to deflect the same and therefore give the same result, the delta that you calculate in each case would have to be the same. So let's look at what EI here at the end is really about. So Young's modulus E, that's basically what E is. So Young's modulus for steel is 3 times higher, roughly, than that of aluminium. And you can think of that basically as an inherent ability of steel chemically to basically resist 3 times faster or better than aluminium in response to any sort of load that's put on it. So as you start bending on a steel structure, it'll build up stresses or resistance, if you like, 3 times faster than aluminium. That is sort of one of the basic differences between steel and aluminium. So if you know that basically the steel here builds up resistance 3 times faster than aluminium, then the only thing you can really fiddle with here in the equation is the I, the inertia, if you like, in each case here. So if it stands to reason that if the Young's modulus of steel is 3 times higher than aluminium, then the aluminium will have to have an inertia which is 3 times higher than the steel one. And that is the reason why typically an aluminium profile will be bigger and have a larger inertia, 3 times typically, than that of a steel profile that does the same job. So that's basically what that means there. So the inertia for aluminium will have to be 3 times that of steel. And once you have that, then these two equations will basically generate the same result, and you will have the same deflection, the same maximum deflection as required by the standard. So that's a basis for this. So in this case, this steel beam here has got an actual inertia of about 4,000 centimeters to the fourth. And the aluminium profile, the 450 mullion as we have it, is about 10,000. Now that ratio is not exactly 3 to 1, but it's approaching that. So it's a fairly good example just to compare the two. So that's typically what you'd have to do here to make aluminium or advantage do the work of a steel structure behind a curtain wall. If we do a few examples here, just in terms of equivalence, it's sometimes hard to imagine exactly what it is. So if you start here on the left-hand side, so the equivalence of a 200 aluminium mullion in advantage, for instance, would be a 60 by 163 millimeter box. So those two would behave roughly the same and do the same thing and behind a curtain wall or in a curtain wall, if you like. By comparison, the 250 here, you need a 180 profile, the 350 to a 270 profile, and the 450 mullion here would be equivalent to a 370 profile. Now, you can't buy relatively nice looking steel sections like that, but you certainly can buy the aluminium profiles or in stock. But what you'll have to make do with in steel is basically this relatively unappealing I-beam or something similar to that. So that's what you end up with. So what Advantage allows you to do basically is to go from a structure like this, which is supported by steel, to a structure like that, where it's just aluminium behind there. And it just gives you a much cleaner set of lines, and it just looks better overall. So that's the basis for essentially the advantage that you get with big aluminium profile. So in summary, curtain walls look better with steel reinforcements. Advantage mullions are big enough to replace steel. The inertia for the aluminium just needs to be roughly 3 times that of that for steel. Point number 4, size does matter, that's for sure. You have to have quite big aluminium profiles to make this possible. And as we know, Advantage is probably the strongest curtain wall around, certainly on the South African market. So with that, I hope you understand the advantages of the HBS curtain wall. Thank you very much.